Hi everyone. Okay, so we'll start today's session. So the first question is, which of the following does not have a multiplicative inverse modulo 6G? So in the last problem set, if you remember, we were mostly talking about prime modulus, but now we are also talking about non-prime composite moduli also. So 60 is a composite number. Let's see, the options are 7, 11, 5, and 13. So, right? Five. So 5. So the answer is 5. And why is that? Because Euclid's algorithm. Hmm? So Euclid's algorithm Euclid's algorithm, or there is a simpler relation. If you're looking modulo n for any n, and if you're looking at an a such that a is, yeah, so you, yeah, so you said the same thing. A is co-prime to n, that is GCD of a and n is 1, then inverse of a exists modulo n, otherwise it does not. Right, this is a simple property that is always true. If a and n have a non-trivial common factor, or GCD of a and n is strictly bigger than 1, then inverse of a does not exist. So here 5, so GCD of 5 and 60 is 5. 5 divided 60. So it is bigger than 1. So that's why uh, inverse of 5 does not exist. But just for, yeah, and 7, 11, and 13 are actually even primes, right? So like inverse of these numbers would exist for most moduli apart from their own multiples, right? But for example, so here 5 divides 60, but even with or maybe not 5, let's say if you're looking mod 12, or maybe even a better, so if you are looking mod 21, 18, right? So GCD of 18 and 21 is 3. So inverse of 18 also does not exist. So 18 doesn't divide 21, but just to make it clear, because yeah, okay, let's move on to the next question. If n is 120, the value of phi of n is, where phi is the Euler's quotient function. So we talked about this last time also.
So this would be 190.
This would be how much?
119.
119? No, because 120 is not prime. Only for prime numbers, it's so phi of p for any prime p is p minus 1. Let me.
I mean, in that case, we have to find the two primes that make up 120.
Yes, that's true. So you have to find the prime factorization of 120. So yeah,
15
so
and 8.
huh?
15 and 8.
What are you saying?
So 15 and 8, can we break it into? Okay, 8 is not prime and 15 is not.
I'm sorry, there is some echo.
So actually, I was saying 15 and 8.
Huh,
15 and 8 both are non-prime. It cannot be correct.
huh. Right. 15 and 8, right?
Yes, sir.
Yeah, that's true. So you can say phi of 120 is phi of 15 times 8, and 15 and 8 are co-prime to each other. Why? Because 15 is like 3 and 5 are the prime factors, 8, 2 is the only prime factor. So these are co-prime to each other. And once we have that, we can write, we know this property that if, write the property below,
So,
phi.
but in that case, 15 individually is not prime and 8 is also not prime. So, why we are
So
considering
let me,
all this?
so that's what I'm writing here. Phi of m times n is phi of m times phi of n. Here, m and n don't need to be prime numbers. They just need to be co-prime to each other. If m and n are co-prime to each other, which means that GCD of m and n is 1. So they don't have any common factor, right? That's when two integers are called co-prime. They don't need to be prime individually. So m, it's not like m has to be prime or n has to be prime, but they need to be co-prime to each other, meaning that they don't have any common factor other than 1. So 15 and 8 don't have any common factor because the prime factors that come up in their factorization are, so for 15 they are 3 and 5, for 8 they are, it's just 2. So there can't be any common factor between these two, right? They are co-prime to each other. So then we can use this
That
property.
means now again we will break that 15 into 3 and 5, and again that
Huh.
8 into 2 and 4, like that.
Yeah. So you can say now, say if this 5 of 15 times 8 is 5 of 15 times 5 of 8, and now you can use 15 is again 3 times 5, and 8 is like 2 to the power 3, right? And again 3 and 5 are also co-prime to each other, so that would become 5 of 3 times 5 of 5 times 5 of 2 to the 3. Now for we wrote, yeah, so we wrote this earlier, 5 of p is p minus 1. So why, for those of you for whom it's not clear why this is the case, I'll just describe briefly. So phi of n are all integers which lie between 1 and n minus 1, such that a and n are co-prime to each other. This is the definition of phi. So for a prime number p, all integers between 1 and p minus 1 are co-prime. That's the definition of a prime number. Are co-prime to it, right? So for any prime p, that's why phi of p is p minus 1 for all prime p, right? Similarly, let's say we consider a prime power. For a prime power p to the k, the only integers between 1 and p to the k minus 1 that have a common factor with p to the k are multiples of p. Does that make sense? Because p is a this is a prime power, and for any other integer smaller than it to have a common factor with it, it needs to be a multiple of p. It needs to have p as one of its factors in the factorization, and every multiple of p will have uh, p common with p to the k, right? So those are the only integers which are not co-prime to p to the k, right? And what's their number?
So
What's
what will be the answer of that 2 to the power 3?
huh?
So what will be the answer of 2 to the power 3? What will put?
2 to the power 3.
Yes, sir.
That's what I'm getting to. Like, let me just give me some more. That's what I'm getting towards. So, yeah. So if you, so phi of p to the k should be p to the k minus one minus how many multiples of p came up in this, right? And that you can find by p to the k over p minus one, which is p to the k minus p to the k minus one, right? Or p to the k minus 1 times p minus 1. So I was just motivating what the answer is. We don't always have to just come up to the answer directly. Just these are all logical things. So this implies that phi of 2 to the 3 should be 2 to the 3 minus 1 times 2 minus 1, which is 2 to the 2 times 1, which is 4. And so the answer of phi 120 becomes phi of 3 times phi of 5 times phi of 2 to the 3, which is uh, 3 minus 1 times 5 minus 1 times 4, which is 2 times 4, 8. It was a 32.
Sir, how did this formula come to the power 3? Can you please
That's
explain
what I
that?
was explaining. That's what I was explaining here. That, sorry. Yeah. So if you have a prime power p to the k, the only, so look at the definition of phi. Like, the definition of phi is all integers between 1 and n minus 1 which are co-prime to a. Sorry, n. So all integers a lying between 1 and n minus 1 which are co-prime to n. The number of those integers, the size of this set, sorry, I should have mentioned this is a set. The size of this set is phi of n.
So like we couldn't do that like phi of 2 into 2 into 2 as because the all the 2's are the co-prime is not co-prime with the.
Yes. So you can't say phi of 2 to the 3 is phi of 2 times phi of 2 times phi of 2, because like 2. So you have these numbers have to be co-prime. So that's why the standard approach is once you have an n, uh, you write the prime factorization of n, p1 to the k1, p2 to the k2, and so on, right? And then you can say directly phi of n is, because these primes are powers of different primes are co-prime to each other, right? So you can, here you can say this is phi of p1 to the k1 times phi of p2 to the k2, and so on, times phi of pl to the kl.
So
And
like
then,
we get these notes in the dashboard in our.
yeah, you do. Don't you have the link for the previous lectures?
Uh, Actually, I couldn't attend that.
But the notes are there. The notes and the video is also there.
Yeah, so I will definitely download that.
Yeah, okay.
Okay, thank you.
Yeah. So here now you can write phi of p to the k is p to the k minus 1 times p minus 1, and so on. Like do this, right? So this is the standard approach for computing phi. But just to describe where this formula came from, for a prime power. So yeah, so for looking at the definition of phi, all integers smaller than the number which are co-prime to it. So for p to the k, the all the multiples of p are not co-prime to it, but other than those, everything is co-prime to p to the k, and that's why phi of p to the k becomes p to the k minus 1. So the number of integers between 1 and p to the k minus 1 is p to the k minus 1 minus all multiples of p which are p to the k over p divided by p minus 1. Minus 1 because p to the k we don't want to include p to the k. So I'm sorry if this is more confusing, but just to motivate why the formula is the way it is. So let's move on to the next question. What is the remainder when 3 to the 4444 is divided by 5? Any guesses? This is such a large number. Like, how does one even go about this? So we can't compute this, of course. Like, we can't even.
So
Right.
here we use to the formula a to the phi
Mm-hmm.
n mod. So that's formula we should use here to get the
Hmm.
answer.
Okay, so you are talking about Euler's,
Euler's theorem.
yeah, Euler's theorem or Euler's torsion formula, whatever. Okay, yeah, let's call it Euler's theorem. So Euler's theorem is if, sorry, if A and N are co-prime to each other, then A to the x mod n is equivalent to A to the x mod phi n mod n, right? So this is Euler's formula. Okay, so how do we use it here? A and n are so first things first, we'll check step by step. A and n should be co-prime to each other. So R 3 and 5 co-prime to each other. The answer is yes, right? Okay, so first condition is satisfied. Second thing, what is phi of n? So n here is 5. What is phi of 5? As we saw before, it's 5 minus 1, which is 4. Now we can do the computation. So 3 to the 4444 mod 5 is 3 through the 4 4 4 4 mod 4 mod 5, which in turn is equivalent to, what should this be in the exponent now? What is 4444 mod 4?
Zero.
Okay, it's 0 because this is
So one answer.
yeah, because it's divisible by 4, so it's 0. So we get
This equation I wasn't able to find that a to the power x mod n. It was there, but I couldn't solve it.
which one?
This direct formula I didn't remember.
Okay. Even then you can solve this question, right? Even without the direct formula. So I'll describe that in a moment. Yeah, so three we get here 3 to the 0 mod 5, 3 to the 0 is 1. Right, so 1 is our answer. We could have thought about this directly also. Like we could have said, okay, let's start computing, right? So 3 we know is 3 mod 5, then 3 square is 9, which is 4 mod 5. Let's compute 3 to the 4. Which is 4 square is 16, which is 1 mod 5. Right? So once you know 3 to the 4 is 1 mod 5, it implies that any power of this is also going to be 1 mod 5, because any power of 1 is 1. So 3 to the 4k is also 1 mod 5 for all k. And 4444 is a multiple of 4. Not hard to see. Therefore, 3 to the 4444 is also 1 mod 5. In some sense, this is what Euler's formula does. Like for every a and n, it does that. Yeah, but this kind of uh, analysis can also be done like without using the formula. Like in case you come up with any 3 to the k, which is 1, sorry, not even 3. Like if you have a general, you know you find a k such that a to the k is 1 mod n, then any a to the x is going to be a to the x mod k mod n. This is not hard to see because you can write x as lk plus b, let's say, or r, right? This is the division, this is the quotient, and this is the remainder. Uh, So you can do this for any x and for any k, and then you can use this a to the lk plus r is equivalent to a to the lk times a to the r mod n, and this is equal to a to the k to the power l times a to the r mod n, and a to the k you showed was 1. So this is a to the r mod n, which is also r is the same as x mod k, right? X mod k and r is the same. So you can do this also. Okay, to the next question. What are the quadratic residues modulo 13? So what are quadratic residues? First of all, so x is a quadratic residue modulo n if there exists. So IFF here stands for if and only if there exists uh, uh, power, let's call the y or m, such that, sorry, not even, sorry. X is a quadratic residue modulo n if and only if there exists a y such that x is equivalent to y square modulo n. It's all the squares modulo whatever the squares are, they are called quadratic residues. So just to specify mod p, there are exactly p over 2 quadratic residues. So for example, if G is a generator, mod P, then all even powers of G are quadratic residues. So we already know that G to the P minus 1 is same as 1 mod P. This is called Fermat's little theorem, right? So G to the P minus 1 is going to be 1, but all even powers before that. So G to the 0 is same as 1, which is also same as P minus 1 mod P. Then there is a G square, G to the 4, whatever up to G to the P minus 3, because G to the P minus 1 is same as 0. So all these are quadratic residues modulo prime P. That doesn't mean that once you are given a prime P, you will go about finding a generator first and then computing the quadratic residues. There is a simpler check to ensure if so yeah, so let's say if X is a quadratic residue.
So can you please scroll up?
Huh?
Sir,
Scroll up.
please can
Okay.
you scroll up?
Okay.
Yes, sir, written.
Hmm. So if X is a quadratic residue, there is a simpler check modulo P. Then note this, right? So for all A, we have that A to the P minus 1 is equivalent to 1 mod P, right? Now for a quadratic residue, we know that X is same as Y square. So what is X to the P minus 1 over 2? What is this? X to the P minus 1 over 2 is Y square to the Y square to the P minus 1 over 2, which in turn is equivalent to Y to the P minus 1, which should be equivalent to 1 mod P, right? So for quadratic residues, you get this special relation, which is not true for other general elements modulo P. So for general elements, this is the relation for all A, but for quadratic residues, you have the special relation that X to the P minus 1 over 2 is equivalent to 1 mod P, right? Now if we use this modulo 13, then we can find things quickly. So for example, so first of all, for 13, uh, P minus 1 over 2 is uh, 13 minus 1 over 2 or 6. So we can verify like element by element. So 1 is always a quadratic residue, right? Yeah, 1 is always, because it's like some generated to the power 0 and 0 is considered even. So 1 and and 1 is 1 square. So you can say 1 is 1 square. So yeah, 1 is always a quadratic residue. So 1 satisfies, let's say 2. So 2 to the 6 should be 1 mod 13. Is it true? If you say, so let's compute this. So 2 to the 3 is 8 mod 13. 2 to the 4 is 3 mod 13, right? 2 to the 5 is 6 mod 13. 2 to the 6 is 12 mod 13. So it is not equal to 1. So this implies that 2 is not a quadratic residue, right? Let's do something similar for others. So 3, we have to check if 3 to the 6 is 1 mod 13. So for that, 3 square is 9, right? 3 cube is 1. So if 3 cube is 1, then 3 to the 6 is also going to be 1. So 3 is a quadratic residue. 4 a quadratic residue. So 4 square is 3, right? So 4 to the 6 is going to be 3 cube, which is 1 mod 13. So while we are at it, let's do it for every one. 5 to the 6. So for that, 5 square is 25, which is minus 1 mod 13, because it's like 26 minus 1, right? Which would mean that 5 to the 6 is again minus 1. It's like minus 1 cube, which is again minus 1 mod 13. So 5 is also not a quadratic residue. I'll do it for each one. So 6 6 square is minus 3. 6 square is 36, which is 39 minus 3. So 6 square is minus 3, which means that 6 to the 6 is minus 1 to the 3, 3 to the 3. But again, there is a minus 1 here. So this is also minus 1. So not, right? Again, 7. Like you can do this for. Yeah, so you can similarly show that you'll have the answer. So 9, 10, and 12. So 9. So for example, yeah. So once you come to the larger elements, let's say 9 to the 6. One easy thing we can do is 9 is also same as minus 3 with respect to mod 13. Sorry, not minus 3 but minus 4. So use that. 9 is equivalent to minus 4 mod 13. So 9 to the 6 is going to be minus 1 to the 6, which cancels out. So it's going to be the same as 4 to the 6 mod 13. So if 4 was a quadratic residue, then it's negative would also be a quadratic residue. Or maybe not for general prime, but for at least this situation, since we had to check, sorry, with an even power, uh, the negatives are also quadratic residues. So similarly, 3 was a quadratic residue, so minus 3 is also, and minus 3 is 10 mod 13, so 10 is also a quadratic residue. Similarly, 1 was 2 wasn't, so minus 1 will also be a quadratic residue, which is 12. So this is also a quadratic residue, right? And since we showed that 5 is not a quadratic residue, minus 5 can also not be a quadratic residue here, because power 6 here won't be 1, because 5 to the power 6 is same as minus 1 minus 5 to the power 6. So that's why 8 is not a quadratic residue. We already know that before computing anything. So I hope that is okay. So I'll just write the answer in case. Okay. So the final question for today. Let a polynomial fx be 5x squared plus 2x plus 3, and gx be 3x squared plus 5x plus 3. Then the degree of fx times gx over z5 is, right? So z5 we already know is the set of all integers modulo 5, right? So this is like z mod 5. So whenever you are doing computation in z over z5, it means that you have to take a modulo 5. That's it, right? So you have to compute fx times dx mod 5. Now here we can use an identity to simplify our calculation. One thing could be to compute the whole thing first and then do a mod 5, right? Let's do that to begin. So let's compute this 5x squared plus 2x plus 3 times 3x squared plus 5x plus 3 mod 5. So this is same as 15x to the power 4 plus 25 plus 6, 31 x cube, yeah, plus 15 plus 9 x square
So
plus,
if
huh?
this star is multiplied,
Huh?
but
What?
star is multiplied.
Yeah, star
Then
is,
you just
sorry.
star of use
So,
karo multiply. No?
sorry, yeah, yeah. Maybe I should call it dot, right? Yeah, this is multiply. You can.
Actually से वो ग्रुप रिंग आजकल बहुत यूज हो रहा था इससे
क्या क्या चल क्या चल रहा था? Is it okay now?
yes,
Okay. Yeah, so maybe I should replace star by dot. Yeah. So I'm just doing the calculation right now. Coefficient of x to the 4 is both coefficients of x square 15. Then x cube is x square and x. 5 5 is 25 plus from here it's 6, so 31. Then coefficient of x square is 15 plus 10 plus 9. Yeah. Yeah. Is there a question? Coefficient of x is 6 plus 15, and coefficient of the zero term is 9 mod 5, which is 15x to the 4 plus 31x cube plus 20, 34 x square plus 21x plus 9. So what would this be? So x to the 4, this term would vanish because it's a multiple of 5, right? Modulo 5, all multiples of 5 become 0. So this would be 0 plus this would be x cube plus
Sir, how x4 is a multiple of 5?
x4 is not a multiple of 5, but 15 is a multiple of 5. So
Okay,
no,
okay,
no
okay.
matter what you are
So,
going to
but you
put,
had,
uh,
sir, you had written Z6 is Z mod 5. So Z5 it should be, no?
sorry, it's not
That's
Z6.
okay.
I have written in a bad handwriting. This is actually Z5.
Okay, sir.
This is also, yeah, it was Z5. So because 15 is a multiple of 5, no matter what you're going to put in place of x, the answer would be 0. So so this becomes 0, this becomes x cube. 31 mod 5 is 1. So you can replace that by 1, right?
And
34
then it will
mod,
be 4x square
yeah, this would be 4x square. This is again
and then
1x.
1x.
This is again 4. So the answer is x cube plus 4x square plus x plus 4 mod 5. So degree is 3, right? But what I'm trying to say is that there is a much simpler way to do this, right? You had fx times gx mod 5. You could have simply done fx mod 5 times gx mod 5 whole mod 5. So we could have taken the mod 5 too within the polynomials also. That would have been much simpler to do. That would have become 5x square plus 2x plus 3 mod 5 times 3x square plus 5x plus 3 mod 5 whole mod 5, right? So now this becomes, so here 5 is a multiple of 5, of course, so it just goes away here only. So you have 2x plus 3 here, and you have 3x square. Again 5x also goes away. 3x square plus 3, right? Here you get 6x cube plus 9x square plus 6x plus 3, which is same as x cube plus 4x square plus x plus 3 mod 5, right? So this was much simpler. You got the same polynomial. No, 3 these are 9. This should be 9. Yeah. So this is the simpler way. Simplify the things before doing the hard part. Is that okay? Any problems?
No, sir.
Okay, good. So there are some different problems that the other TA discusses in the next session. So you are advised to attend that from 7 onwards, and we can end this session now.
So I have a question regarding that.
Okay.
So like as we like the Fermat's-Little theorem, just give me yeah, तो जैसे फॉर्मस-लिटिस थ्योरम से हम लोग यूलर क्राइटेरियन का जो रेसिड्यू क्वालिटी रेसिड्यू निकालने का तरीका है उसे वेरीफाई
Uh-huh.
कर सकते हैं. So did we verify that through Fermat-Littis theorem of getting the quadratic residue? Like that are almost same. Like after putting the value, we only get the e to the power p minus 1 equals to 1 mod p.
Uh-huh.
So वो दोनों सेम हो जा रहा है. तो जो क्वाड्रेटिक रेसिड्यू का है और जो फॉर्मल-लिटिस थ्योरम है वो दोनों सेम ही है.
नहीं नहीं, so Fermat's little theorem is this part, right? This is Fermat's little theorem, right?
Exactly.
Now I'm saying for quadratic residues, you get something more than what you get for all elements. You have some an extra relation here that you can use.
Definitely, like by putting the value, we are getting the formal-Littis theorem in the quadratic residue.
Huh, you are saying by putting x equal to y square.
Yeah,
Yeah, so by putting x equal to y square, you get the same as y. But this is still a relation you can verify, right? For you started with an x, which was a quadratic residue, and you proved that x to the p minus 1 over 2 is same as 1 mod p. Now this is not true for all x. Fermat's little theorem holds
so
for
there is a
all a,
condition.
right? Fermat's little theorem holds for all a, but this relation here is not true for all x, but only for quadratic residues. For example, here you put x as y square because x was a quadratic residue. So y to the p minus 1 is 1. That's the Fermat's little theorem. But y to the p minus 1 over 2 may not be 1. You don't know that. But x to the p minus 1 over 2 is 1 because x is a quadratic residue. For y we don't know. So for y we can't say this. This we can't say for y. May not hold for y. Right? Is that okay?
Okay.
Yes, so if there are no more questions, we can end this session and please attend the next one also.
Sir, can we shift the session timing to Tuesday because both of them at same continuous hours is a bit taxing.
I know, but like it's even we try to the PM, so the authorities they are not in to change the timings now anymore. Like they could have done that initially, but not now. Yeah,
Yes.
like it's not just up to me. There, so they have I have to teach in this fixed slot only. Okay,
Okay, sir.
so thank you. Have a nice day.
Okay, sir.
Yeah, bye bye.